All right, folks, now that we have reviewed exponential functions, section 4.1, and logarithmic functions, section 4.2, it's time to discuss the calculus of those functions. So section 4.3, we're going to focus on the derivatives of exponential functions. In section 4.4, we'll focus on the derivatives of logarithmic functions. So here in section 4.3, the objectives we're going to focus on will be how to differentiate an exponential function that involves e to the x. In section objective number 2, we're going to differentiate an exponential function involving e raised to some function of x. So this is going to bring out the chain rule. And then the third objective we'll look at is we're going to apply the derivative of an exponential function to an exponential growth model. I didn't know if I wanted to do a growth model or decay model. I decided that we'd look at a growth model. So this is the derivative of the exponential function. So if your function is f of x equals e to the x, the derivative is e to the x. Seems kind of weird, maybe a little trippy. It is a function that is its own derivative. I would encourage you to read pages 267 to 268 in your book on the derivation of the derivative of e to the x is e to the x. I just want to practice this concept. So this is a new derivative rule. It seems like it's a pretty friendly derivative rule. The derivative of e to the x is e to the x. So this first example, we're going to differentiate the following functions. The first one is part A, f of x equals x cubed times e to the x. Part B, the function is the quantity e to the x plus 6 raised to the third power. And then part C is x cubed over e to the x. So write these down. I'm going to head off to the chalkboard and going to work through the derivatives of these three. All right, here we go with a little calculus in this chapter. So in this example, we are asked to differentiate. It gave three parts, A, B, and C. So in part A, we're asked to differentiate f of x equals x cubed times e to the x. So the one new rule that we have right now, the amazing thing, that the derivative of e to the x is e to the x. But notice here in this first one, part A, notice that the function given is a product of two functions. That means we need to use the product rule. So remember your product rule. The product rule says the derivative of the first function, so that's 3x squared, times the second function, plus the first function, times, now the derivative of the second function. Well, the derivative of e to the x is e to the x. That's it. Part B, you were given the function g of x equals the quantity e to the x plus 6 raised to the third power. So here we need to use the old chain rule, the derivative. So remember outside, inside. So the derivative of the outside function, 3 e to the x plus 6 to the second power. That's the derivative of the outside. Now times chain rule times the derivative of the inside function. So the derivative of e to the x plus 6, well, the derivative of e to the x is just e to the x. And the derivative of 6 is 0. So that's it. Part C, the function is x cubed over e to the x. So here we need to use the quotient rule. So remember the quotient rule. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Derivative of e to the x is e to the x. All over the denominator squared. Or, I could write that. I could write the denominator as e to the 2x. E to the x squared is e to the 2x. So before we go on, before we, maybe shift this into third or fourth gear, I'd like you to practice a couple of these types of derivatives. So here in section 4.3 exercises, I'd like you to pause the video. I'd like you to do exercises 14 and 16 here in section 4.3. After you've done them, restart the video, and we'll see if you got them correct. All right, in number 14, you were asked to get the derivative of the function 10x squared e to the x. Again, this looks like a classic product rule. 10x squared e to the x. The first function is 10x squared. The second function is e to the x. So when we crank this through the product rule, it's the derivative of the first function, which is 20x, times the second function, plus the first function, times the derivative of the second. Well, the derivative of e to the x is e to the x. And that is it. For number 16, you were asked to differentiate the function, the cube root of e to the x plus 5. So yeah, the first thing I would do here is algebra and rewrite the cube root as the exponent of 1/3. Now I compute the derivative. I'm gonna have to remember the chain rule here. So the derivative. So the derivative of the outside function, 1/3 e to the x plus 5 to the negative 2/3 times, okay, now the chain rule, I have to multiply it by the derivative of the inside function. And the derivative of e to the x plus 5 is just e to the x. Remember, the derivative of a constant is 0. And that is it for number 16. So hopefully you got those two. Let's head back to the slides and see what's next. All right, as that example and the couple of practice problems I asked you to do illustrated, differentiating an e to the x isn't bad. We also reviewed some old rules that we need to remember, such as the product rule, the quotient rule. Now it's time to look at the chain rule for the exponential function. So if f represents a differentiable function of x, then the derivative of the composition of functions, h of x equals e to the f of x. So just think e has an exponent that is a function of x. Maybe it's x squared, or maybe it's 2x plus 3. Maybe it's 0.4x. It's just the exponent is a function of x. It's not just simply x. So when it has that form, the derivative, h prime of x, well, it's e to the f of x times f prime of x. So in other words, if your exponential function is e raised to some power, raised to anything, raised to some function of x, the derivative is e to that function of x times the derivative of the exponent. That's what f prime of x is, the derivative of the exponent. Chain rule with exponential functions, actually pretty friendly. So let's practice. In this example, we're going to get the derivatives for part A, h of x equals 7e to the 5x plus 8. Part B, f of x equals 10e to the 2x squared plus 9x. Part C, f of x equals e to the 0.342x. And then in part D, f of x is 1.31 e to the negative 0.42x. So get this written down. I'm going to head off to the chalkboard. We're going to work through all 4 parts and hopefully see that it's not too bad. All right, in this example, we're going to practice using the chain rule for exponential functions. In other words, when the exponent of e, it's something different than just x. It's actually some function of x. So in part A, we're given the function h of x equals 7e to the 5x plus 8. So the derivative starts off 7, it's the constant 7, e to the 5x plus 8 times, now it's just the derivative of the exponent. The derivative of this exponent, the derivative of 5x plus 8, is just 5. Or if you prefer, you could say 35e to the 5x plus 8. So it looks very similar to just differentiating e to the x. So when you have e to some, I'll say junk, e to some junk, the derivative is e to the junk times the derivative of the junk, the derivative of the exponent. Part B, your function is 10e to the 2x squared plus 9x. So your derivative here starts off the same, 10e to the 2x squared plus 9x. Now the chain rule, times the derivative of the exponent. Well, the derivative of the exponent is 4x plus 9. And note how I put that in parentheses. F, the function is e to the 0.342x. So the derivative is e to the 0.342x times the derivative of the exponent. Well, the derivative of the exponent is 0.342. And there was a d. I'm sorry, I didn't write that up here. Let me write it right here. d, f of x equals 1.31 e to the negative 0.42x. So for this one, the derivative is 1.31 e to the negative 0.42x times the derivative of the exponent, which is negative 0.42. All right, so let's do a little bit of practice. I want you to do a little bit of practice here with the chain rule. So I'd like you in section 4.3, pause the tape, pause this video, and the 4.3 exercises, do numbers 24 and 28, and then you know the drill, restart the video, and I'll be here at the board working through them. Hey folks, here in number 24, we were asked to get the derivative of f of x equals e to the 6x plus 9. So here we go. The derivative is e to the 6x plus 9 times the derivative of the exponent, which is 6. That's it. Maybe you wrote it as 6e to the 6x plus 9. That's fine. They're both the same. But that's it for number 24. In number 28, the function is 2x cubed e to the 6x squared. All right, I got to take care here because I see a product of two functions. So I know I have to use the product rule. So here I go with the product rule. Remember the product rule. The derivative of the first function, that's 6x squared, times the second function, plus the first function, times, all right, now the derivative of the second function. Well, the derivative of the second function starts off as e to the 6x squared. Then we have to remember the chain rule, times the derivative of the exponent. And the derivative of the exponent is 12x. And yeah, I could simplify that down. I could do some factoring. There's the greatest common factor of 6x squared e to the 6x squared that I could factor out, but I'm not going to bother doing that. So I want to get back to the slides and see what is next. All right, folks, now that we've learned how to differentiate exponential functions, I think it's time to look at an application. So in this example, let's see, we have the number of Android apps can be modeled by the exponential function f of x equals 2.01 e to the 0.159x. Here, x is the number of months since December 2008, and f of x is the number of apps in thousands. So we're going to evaluate and interpret f prime of 30, and we're going to compare it to f prime of 35. So make sure you write this down because I'm going to head off to the chalkboard. First thing we'll have to do is get the derivative, f prime of x. Then we'll evaluate, interpret, and we'll be good to go. All right, this example was an application. Should have written it down. There were a lot of words. That was the function you were given, and x represented the number of months since December 2008. And f of x represented the number of Android apps in thousands. So we're asked to evaluate and interpret f prime of 30 and compare it to f prime of 35. So let's get started here by first just getting the derivative. So the derivative is 2.01 e to the 0.159x. Then remember the chain rule, times the derivative of the exponent. So let's see, f prime of 30. All right, so when I toss 30 in here for the x, I get f prime of 30 to be about 37.69. I just rounded to 2 decimal places. So now what does this mean? All right, so I had to think about this a little bit. X is the number of X is the number of months since December 2008. So 30 months since December 2008 would be June of 2011. So this means in June 2011, the number of Android apps was, okay, it's a positive number, so that means it was increasing at a rate of, all right, so f of x is the number of apps in thousands. So this is 37.69 thousand. So I'm going to write that as actual number. I'm going to move the decimal point to the right 3 places to say at a rate of 37,690 apps per month. All right, let's do f prime of 35. So when I put 35 in here for the x into the derivative, and I do f prime of 35, I get, use my calculator, and I get 83.45. Okay, so 35. It's the number of months since December 2008. I think that would be November of 2011. And I'm not going to write down the interpretation because it's almost exactly the same as this, except here it would be in November of 2011, the number of Android apps was increasing at a rate of 83,450 apps per month. So, I mean, it's increasing at a faster rate. So that's it. That was an application. I'd like you to practice one real quick before I turn you loose. So in the section 4.3 exercises, I'd like you to pause the video, try number 54, restart the video, I'll be here at the board, we'll make sure you have it correct. Alright folks, number 54, I'm not going to read all the words, just the highlights of it. It's talking about the Facebook revenue. It exhibits exponential growth. That's the function that models Facebook revenue from 2005 to 2010. X is the number of years since 2000, and f of x is Facebook revenue in millions of dollars. So part A, determine the derivative. So here we go, part A. The derivative is just simply 2.78 e to the 0.6x times the chain rule, the derivative of the exponent, 0.6. Okay, now in part B, part B we're asked to determine the rate of change in Facebook's revenue in 2009. So let's see, X is the number of years since 2000. So 2009, that corresponds with an X value of 9. So I need to evaluate the derivative at 9. So I put 9 in for the X, and when I use my calculator, I get 369 I rounded it to 369.306. So that meant in 2009, the rate of change in the Facebook revenue was about $369.306 million per year. Hey, wow. That's it for number 54. So this concludes section 4.3. So you're all set. Do all the exercises in section 4.3 because that's all there is to the section. So go do the exercises, and thanks for watching.